Okay, this is our study guide for our Newton's Laws test, which is on Thursday. Okay, so this is an object moving at a constant velocity. What must be true about applied force and force of friction? So this is moving along maybe a tabletop, and if it's at constant velocity, our forces have to be balanced. So that means that applied force has to be equal to force of friction. Maybe there's some of each. If applied force is greater than friction, then what must be true about the motion of the object? It's accelerating. Somehow it is speeding up or slowing down, but its velocity is changing if those two forces are not equal, because that means we have a net force. Remember Newton's second law, F net equals mass times acceleration. Okay, object at rest on an inclined plane. So we did a lab with the inclined plane where we looked at an object we looked at our carts on the planes. And so for this object, we have a normal force that's perpendicular to the plane, so it's at a right angle to the plane. We have a force of gravity that's pointing straight down towards the earth. And then if we have friction, it's pointing in the opposite direction back up the plane, because this is going to slide down in this direction here, and so friction is going to be in the opposite direction of that. What ends up happening with this, since force of gravity is at an angle, we call this our y-axis, we call this our x-axis, and then it's components of the force of gravity that cause our object to move down the plane in the x, and then a component that balances normal force in the y. Okay. But these are what you need to know in terms of the forces. I'll label x and y as well, but that's it. So what's the net force acting on the object, and how do you know? It says this object is at rest. Okay, so that means that net force is going to be 0. And I know that because of Newton's second law. The object is at rest, which means it's not accelerating. And so that means F net also has to equal 0 because of math. I mean, if this is 0, 0 times some number for the mass is still going to give me 0. Okay, what a person's weight is 700 newtons on Earth. What is their mass? So we can use this equation, Fg equals m times g. Fg is my force of gravity, or my weight. And if I weigh 700 newtons on Earth, I can do mass times 9.8. 9.8 is g, my acceleration due to gravity, and then I solve that for mass. Okay, so I don't have my calculator right nearby. I have to grab it, but for now I'll use my phone because it is nearby. 700 divided by 9.8 is 71.4. So 71.4 kilograms is my mass. Okay. And then how about on the moon? What's their weight on the moon? Okay, so the moon has less gravity than the Earth. The moon has a G of 1.63 versus 9.8. If I want their weight on the moon, I can do Fg equals m times g equals 71.4, because I just got that earlier, times 1.63. Okay, so again, handy dandy calculator, 71.4 times 0.63 equals 116.3. So 116.3 newtons on the moon versus 700 newtons on the Earth. That's a pretty big difference. So, okay, we got a skydiver. They experience 400 newtons of air resistance, and we want to draw a diagram and determine their acceleration. Okay, so I'm just going to draw my skydiver as a box. They're an 80 kilogram skydiver, so that means they've got a force of gravity of 80 times 9.8, just m times g again. Remember, we've done that a lot of times now because we always start with that. Whoops. 80 times 9.8 equals, no, times, that's why I don't like using my phone calculator, 784 newtons, okay. And then she has air resistance. This is going to be pushing in the opposite direction of 400 newtons. So here's my free body diagram. I got force of gravity pointing downwards. I got air resistance pointing upwards. So like that's pushing up on her as she's falling. So the net force is going to be 784 minus 400. Gives me 384 newtons. And then my acceleration is going to be 384 newtons divided by her mass, which is 80 kilograms. That's, again, going back to Newton's second law here and solving for acceleration. So 384 divided by 80 is 4.8. So she's moving at 4.8 meters per second per second. So whereas we're in free fall, we're doing 9.8 meters per second per second. Hers is slowed down because there's air resistance pushing back on her, which we usually ignore air resistance, but in this case we did not. So, but that is okay. All right, let me try and do a few more. I don't know how much time I've spent on this video. All right. An object with mass of 3 kilograms is hanging from a string at rest. Draw the free body diagram. What's the tension value in the string? So again, we've got an object. It has a force of gravity of 3 times 9.8. I'm just going to round that to 10 for right now. So about 30 newtons. If it is at rest, that means my forces have to be balanced. So the tension on the string has also got to be 30 newtons because these two forces have got to be equal value and opposite direction if I'm at rest because I'm balanced. Okay, a 4 kilogram block is pushed with 10 newtons to the right. It has 4 newtons of friction. What's the acceleration? So my block has forces, normal force and gravity in the vertical direction, and they're balanced because it's being pushed. I'm assuming it's a horizontal surface. It has a 10 newton push to the right, 4 newtons of friction to the left, and I want to know what the acceleration is. So with this, I know my net force is going to come from these two forces. I'm going to have 10 and 4, so I'm going to do net force equals 10 minus 4 is 6 newtons, okay? And then I can get my acceleration by taking that net force, and I'm going to divide it by the mass. The mass here is 4 kilograms, okay? And that's going to give me my acceleration. I could figure out Fg and Fn also, but I don't really need to in this particular case because all my forces are the applied force and the net force, and that gives me 1.5 meters per second per second. Okay. How much does a 20 kilogram mass weigh on Earth? How much on Mars? So this is similar to the one we did on the other side. We're using Fg equals m times g. So on Earth, I'll just put an E here for Earth. I'm going to have 20 times 9.8, and then on Mars I'm going to have 20, again, same mass, times 2.8, because Mars is smaller than Earth. It has a smaller G value. So 20 times 9.8 is 196 newtons. And then 20 times 2.8 is 56 newtons. So less weight on Mars than on Earth. Okay, last one for this video. A wrecking ball is held by 2 vertical cables. If each cable holds an equal amount of weight, what is the tension in each cable? So here's my wrecking ball. Here are my 2 cables. And I got tension in each one. And then I've got a force of gravity. And my pen's running out. How annoying that it would do that right at this moment. Hang on a second. Figures. Okay. Alright, so force of gravity. And this says it's held by 2 vertical cables, so it's held at rest. So my 2 tensions, 2 times T, has to be balanced by my force of gravity. And then my force of gravity is 300 kilograms times 9.8, which is 2,940 newtons. So each of these cables has got to be holding half of that, because there's 2 of them. They're holding equal amounts. So 2940 divided by 2 is 1,470 newtons. So this force of gravity is offset by these 2. They each have basically half of this force of gravity value that they're holding. Okay, I will stop there and pick it up in the next video.